Okay, now we are recording, and I can also make this full screen, I think. View. All right, so I hope that you guys can see the screen properly, both in the classroom and online. We will get started with exam 1 statistics. So exam 1 has been graded. The grades have been posted on Gradescope. The solutions are uploaded on Piazza. So you have about a week to submit regrade requests by email. So do that by email directly to me, and I will address those after a week after I collect all the requests. Numbers look pretty good. We had 3 perfect scores. That was amazing to see. 18 people above a 90. So almost all the classes above a 70, which is very good to see. But there are certainly some low scores that we need to address, right? So one thing would be what is the reason for a low score? So clearly there are a good number of students who have got the material, understood the material. So what is the reason for a low score here? I want to figure that out. Next, I want to figure out what I can do or the TAs can do to help you sort of improve your grade in the class. So these kind of conversations, whether you want to have them during office hours or do you want to set up a one-on-one meeting with me, let me know using WebEx Teams, and we can set something up. The average was very healthy, 81 points. And then the median was higher than that. You can clearly see the scores tending towards the high range there. So all in all, good news as far as I'm concerned. Questions or concerns here? So on the exam, right, so there are some things that you really cannot miss, right? So the questions about MIPS and CPI, those are just like changing numbers, going through a bunch of calculations and done. So almost all of you got that right. But then in the short answer part, there were a lot of students who missed the points there in the first 40 points short answer questions. So try to look at the solutions, see where we missed things, because we are going to have to revisit those for the final. All right, I think that's enough of that. Let's get into the lecture. Okay, so all those who are attending, you chose the perfect lecture to not miss. This is an important one. This can get a little bit confusing, and my goal is going to be to try to bring as much clarity as I can so that you guys get this. I'm referring to the register forwarding technique, not the stalling technique. Stalling technique is fine. Insert, no operations, and get done. There's no confusion there. But register forwarding can get a bit messy. And this is specifically to avoid a data hazard. So a data hazard is what? You're writing to a register and then you're using that same register as an operand in the next instruction or the instruction following that, right? So you're talking about the 2 instructions after, write use hazard or write use hazard. So these are your 5 steps. You've seen this before. The instruction lifecycle starts with your instruction fetch, instruction decode or register file read, followed by execute or address calculation, memory access, write back. That completes your lifecycle. Now in the execute stage or the address calculation stage, you're executing arithmetic or logical operations, whether they be integer or floating point instructions. But address calculation refers to either calculating the target address for load or store word instructions, or it may be a branch instruction. So you're computing the branch address there. So for example, if I zoom in here, this is being used to compute the branch address. However, this is being used to calculate the target address for the load and store word, right? You're taking the base address, adding the offset, and so on. So that's happening using the ALU here, but the branch address is being computed at the output of that adder, like shift by 4 and add to PC plus 4 and so on. So you've seen these things a few times already from data path conversation. So this should not be such a new thing, right? This is hopefully not a new thing. Then what did we do? We started putting pipeline registers in the middle of each of these stages, right? We had 4 pipeline registers. So we did that pipeline architecture. We had the 5 stages, and in the middle of each of those, we added an IFID pipeline register, IDEX pipeline register, EXMEM, and memory write back. Those 4 pipeline registers were added to our architecture so that we can have multiple instructions in the pipeline, right? So that we are able to use the same hardware for more than one instruction at the same time. Clearly, if you're going to be doing that, then you're going to, because you're using hardware resources, then you're going to need some place where you can store, right? Some buffering. That's what they are being used for. As long as a particular instruction is getting executed, I would want to hold on to the things that are relevant for that instruction. And for that purpose, those pipeline registers were helpful. We saw that in the previous class. Not just for data path, but also for the control, right? All the yellow things, Zach doesn't like the yellow, I know, but I don't have time to change all the colors. But that's, yeah, control signals over there. For IDEX, use the execute stage related control signals there, drop it, continue with the write back and memory. Use the memory, continue with the write back, and done, right? So as long as the instruction is going on, those control signals are also being kept. Now, let's focus on data hazard. How do you avoid them using register forwarding? So that's the crux of our lecture today. How do you avoid data hazards using register forwarding? So the problem was simple. You are trying to write to this particular register here. You are writing to a register and then using the same register immediately in the next clock cycle as the next instruction. And if you are doing this in a non-pipelined architecture, we are fine. Do this, and then you're done, and then do that, you're done, no problem. Because whatever you have updated S0 with, the new value is going to be ready for the next stage, right? So you're going to be okay there. However, if you are going to be doing it in the pipelined manner, then the new value, the updated value of S0 will not be ready for the next instruction to use. You can see this. This is where you will write S0, right? That's where it is writing. You go through that's an add instruction, right? So you will take this, you will add them at the ALU. You don't need to do any data memory access. And then you will write to the register file to S0. So you are writing way over here, right? Which is going to start at, 8 nanoseconds, finish at 9 nanoseconds, right? So it's happening later in time. However, we are trying to use the value of S0 for the next instruction, which is subtract, right here. That's your register access. You're trying to read it here. You're not going to have that value because you're going to have what? An older value, right? So it's not like you're going to have a critical error, stop, nothing of that sort. It's just going to use an older value, but in terms of your calculation, you're not going to get a desired result. So that's your problem, the data hazard. That's specifically for a write use situation, or it might be for write use, because even if there was another instruction over here which was using S0, this would still move to this, right? But again, that's before we do that writing. So new value is not going to be updated over there. That's specifically the reason why we are talking about 2 instructions out, right? We don't talk about third, fourth, only 2 instructions out. That would also be a data hazard, but it would be a different type of hazard. And we'll try to classify them. What are they called? When the data hazard is in the next one, or when the data hazard is in the one after that. We'll talk about those. Okay, so we'll try to look at a pipeline diagram over here. On the left, we have program execution instructions in that specific order. Load word first, then subtract. And then on the x-axis over here, you have time in clock cycles. So clock cycle 1 all the way to clock cycle 6. Load word instruction or subtract instruction or any instruction is going to have those 5 steps: IF, ID, execute, memory, and the write back. So you have all those things applicable for any instruction. However, in clock cycle 1, what are you doing? You are reading the instruction memory. Remember, reading, we are assuming that right half, when it is shaded, that's how we are referring to it as a read operation. And then left half being shaded, we are referring to it as a write operation. So you've got read the instruction memory, get the instruction, write it to the IFID pipeline register. That completes clock cycle 1. Clock cycle 2, read from the IFID pipeline register, read from the register file for the operands, write to the IDEX pipeline register. And you keep going, right? Read from here, do the ALU, write here. Then read from here, write or read. In this case, we are doing a load word instruction. So we are just reading the data memory here. And then write here. Last one, read from here and write here. Yeah. So the entire pipeline register is being shaded because you're reading and writing to it, right? So everything is shaded there. Similarly for ALU, you're shading everything over there. However, for instruction memory, you will only be reading instruction memory. You will only be reading register file here. You will only be writing register file there. This could change, right? This could change depending on load word, store word, or in this case, no shading at all. Why? Subtract instruction. It's an arithmetic instruction which doesn't have anything to do with a memory access, right? So you bypass that stage. No highlighting over there for data memory. So that's how we are indicating it in a pipelined architecture for load word over here. And then immediately after the instruction memory, instruction fetch stage gets done, we start bringing in this subtract instruction into our hardware, right? 2 nanoseconds later, subtract instruction is using those hardware resources. Now, using this, let us try to answer some simple questions here. First, how many cycles does it take to execute this code? Well, you're starting here, you're ending here, so there are going to be 6 clock cycles to execute these 2 instructions. So I hope you guys agree with that. And then, how about this? What is each instruction doing in each clock cycle? Now, there can be several specific questions related to this, right? So I can say, what is load word doing in clock cycle 3? What would you guys say? What would be the first instruction doing in clock cycle 3? Good. Getting the target address, right? So I'm going to get the base address from here, offset address from the immediate field. I'm going to be adding them. So I'm going to be computing that target address. Similarly, you could extend that to any of these 2 instructions for any of these clock cycles, right? For example, you can say, what is the subtract instruction doing in clock cycle 5? Well, I'm just bypassing the data memory, so I'm not doing anything over there for the subtract instruction. Now, so that's how you would answer this. Next, do we have a hazard or not? How are you going to talk about that? Think about answering this question looking at the instructions versus looking at the pipeline diagram. Would you be able to answer this question if you look at the pipeline diagram? Okay, so this is a hazard. It can be any hazard. You have 3 of them. So go ahead. Oh, that was a good fake, man. Uh, so you have three hazards, right? So you've got the data hazard, you've got a control hazard with respect to branching, and then you've got your structural hazard. Structural hazard is use of the same hardware resource by two different instructions, right? So it's the hardware resource contention. That you can answer. That you can answer if you look at the pipeline diagram. You see, only instruction memory is used. Register file, memory, no problem. ALU, register file, different. Memory, ALU, different. Register file, memory, different. Register file, right? So at least in terms of the structural hazard, you will be able to comment about that looking at the pipeline diagram. However, for data hazard, no. For control hazard, no. You would need to go into your instructions. Look at the specifics. What is happening here? Well, you're writing to which instruction? You're writing to 10, right? Register number 10 is what you're changing. You're taking the contents of something in memory. Where in memory? Take the base address in $20, no, $1, add the offset of 20 to it. That's your target address. Go look at whatever you have over there, bring that into register number 10. So you're changing 10, but you're not using 10 here, so you're fine, right? So no data hazard, no control hazard, there's no branching happening here, and then there's no structural hazard as well. So no, there's no hazard here. All right. Now let's take a look at an example. Remember our goal for today? We are trying to avoid data hazard using forwarding, right? That's our goal. So in order to discuss this, we need to create the problem first. What is the problem? Data hazard. So let's try to take an example, look at an example which has a data hazard. So we have some initial values for three registers. In register number 1, we have 0, register number 2, you have 2, 10, and then in register number 3, you have the value 20. Now, what are you doing? You are going through these set of instructions in which register number 2 is either a destination or it is an operand. Now, if you look at the first one here, it is functioning as a destination. So you're changing the contents of register number 2 over there. However, after that, use, and use, right? So after that, register number 2 is only being used. It is not being changed. My goal is to track the value of register number 2 all the way down. So if you're doing this, the first instruction, what is the new value? Well, 1 is 0, 3 is 20, subtract them, put it in $2. So that would be $2 is negative 20, right? So that's the value that it got updated to. It was 10, it got updated to negative 20 after the second instruction got executed. And after that, you are not changing the register 2 anyway, right? So all over here, $2, register number 2 should have only one value, negative 20, which should be used for all the other instructions, right? Yeah, that would work well if it were a non-pipelined architecture. That would be the case. However, this is a pipelined example. That would be a problem. Write, use, you know it's a problem. Write, use, you know it's a problem, right? We look at two instructions out. We have problems here. How do we look at it in a little bit more detail? By going through the pipeline diagram. So we have all those instructions listed over here, subtract and or the same ones, in which register number 2 is either the destination or the operand. So in this case, it's the destination. Everywhere else, it is an operand. And then, depending on that register, number 2, we have highlighted in red what it is being used, where it is being used in each step, in each instruction. So for example, $2 is being written to in the first instruction. That happens there. $2 is an operand for the next instruction. You read it from here. $2 is an operand here, so you read it here. $2 is an operand here and here, you read it here. $2 is a base address, you read it here. right? So you're reading it from the register file in all those instructions. However, you're writing to that register file right in the first one, right? Now, if you see, these are the same resource, right? It's just being used for a different instruction, but it's not like you have different instruction memories. You don't have 5 instruction memories. You have the same, only one hardware resource. We are just drawing it 5 times to show how they are being used for each instruction. At the top over here, we have time in clock cycles, clock cycle 1 all the way to clock cycle 9. And in each clock cycle, let us try to evaluate the value of what is in register number 2. So what do you guys think for clock cycle 1? Well, I have not changed it, right? I have not changed the value of clock cycle register 2 here. So it would be what? Whatever I initialized it to. I think it was 10. Yeah? Clock cycle 2, does it change? No, doesn't change. Clock cycle 3, doesn't change. Clock cycle 4, doesn't change. Clock cycle 5. You see, clock cycle 5, you are writing over here. Yeah? So this, I may be able to say that it is, what is that? Negative 20. So that change happens after, in the clock cycle 5. The only thing that I have to be careful about is that if the clock cycle 5, if the write operation was assumed to be on the right half, then it would create some problems for this guy. The same register file being read, 2 instructions later. So that's why you write here and then you read here, you are going to be okay. Now, after clock cycle 5, what do you have? You will continue with negative 20, right? You will use the same value after that because it's not going to be changing after that. You're not doing a register write ever after that. You're only doing a register write over here. So you guys okay with these values here for clock cycle 2? Register number 2 for all clock cycles? Yeah. Now, if you start looking at the subtract instruction, okay, now we know that it is changing there to negative 20. How about the AND instruction? What is the AND instruction using? $2, 10, wrong. Well, not wrong, previous value, right? That was not intended. How about OR? $2, what is it using? 10, old value. This guy, okay, that is fine, right? So we were okay over here and here, but we had a problem here and here. What was the problem? The contents of register number 2 were the old value, not the new value. So now, so I hope you guys are okay with the problem here. Problem okay? Let's talk solutions. Think wishfully. What do you wish happened such that $2 over here actually used negative 20? What do you think should happen? Go ahead. Okay, so that's okay. Delay is stalling, right? Insert a no operation. So if you inserted no operation, this guy would move here, right? I would need 2 no operations then. So if I move it here, then I'm okay. So I would have to insert 2 NOPs or stall the pipeline, a solution, but it's not the best solution. All right, Andrew, give me 1 second, Zach. Go ahead. There it is, right? So here, Zach, where are you going there? Okay. So you guys are absolutely on the right track. This negative 20, when is it being computed? It is being computed here, right? That is when it gets computed. And immediately after it gets computed, where is it written? It is written onto this EX mem pipeline register, right? So it is computed and written to that. Where do we need it? We need it over here, right? After you get $2 is what? RS, right? So if this is RS and RT, so this guy is what? $2 and this guy is $5, right? Because this is $2 and this is $5. You don't, it's okay if you read the old value here, as long as you take whatever you have written over here to the XMEM register when the first instruction was going on, you forward that over here. Let me draw it nicely. There it is. Instead of using the old value, you can still read it onto this. However, I will have to make a selection. The selection is what? Do you want me to use this or do you want me to use this, right? Muxes. Yeah, exactly. So I will need to use muxes to do that selection. Yeah? Go ahead. We will not be able to do that. So we'll have to use, so next class, after the break, we look at the load use hazard. So this is write use hazard. Load use hazard cannot be solved by this, unfortunately. So we need some other mechanism to deal with load use hazard. But yeah, you're absolutely right. Load use cannot be done using this, just this. Let's see. Okay, so we are done with that, yeah? Also note that if this $2 was over here, we would still be doing the same thing. Instead of forwarding here, we would be forwarding here, right? Instead of RS, we would be doing it for RT. What should I call this? I will call this XMEM forwarding. I'm forwarding the contents of that specific field from XMEM pipeline register to the execute stage. You guys see that? So that's called XMEM forwarding. XMEM forwarding will solve the hazard. What type? Data hazard. But what specific type? It's called the execute hazard, because the hazard, it is happening for the next instruction, right? That's execute hazard. Next, so you guys okay with that? How do we solve that? Now, how about next one? We need to still solve this, right? What do we do for that? We can still do forwarding. Where do we need it? We need it here. Here. We need it here. So where should we forward it from? Should we forward it from XMEM or what? Good. Mem right back. So I can do it from mem right back. So for one instruction out, I'm going to forward from the XMEM forwarding register. For two instructions out, if there is still a data hazard, then I'm going to forward from the mem right back. Mem right back forwarding register, a pipeline register. So that would be called what? Mem right back forwarding. Go ahead. Because that is changed because of this guy, right? So that changes after this guy writes onto this. Right? It's the same hardware. So once this guy uses it, you have lost that. The only place it is left is mem right back. Good question. You guys see that? So how we can do this? With two types of forwarding. You've got the XMEM forwarding and then the mem write back forwarding. XMEM forwarding solves one instruction out. Mem write back forwarding solves two instructions out. All right, so let's, after that, I'm done. After that, I don't need any forwarding. So I need selections, right? Selections were that muxes, right? I need a mux to be able to select from three things. One, no hazard present. So whatever you read from here, use it. Whatever is going through with the instruction. That's when no hazard is there. So that's one case. Second, there is an execute hazard. So do XMEM forwarding. Use the value from here. That's your second option. Third option, memory hazard is present. So use it from the memory write back forwarding register. Right? So those are your three options. So it's not like a really good, four options where you could have two select lines. Here you have to choose one from three. You still need two select lines. You guys okay about this? Now, we need all of this selection for how many things? Here, we also need it for here, right? So we need it for the two things, RS and RT. So we need two of them, duplicates of those muxes. All of this will make up our forwarding unit. So now you have got data path. On top of data path, we had the yellow control lines. And then on top of that, we are going to have a forwarding unit. Questions before we move forward? Okay. So this is your solution, right? So this is inserting knobs. So if I insert knobs, insert two knobs, don't worry about the offense here. So two of them, right? I would need two knobs because I have one, the next instruction from the reference, from the right instruction, I have the one, and then I have two instructions getting affected because of that. So I need two knobs there. If I have two knobs, that's it. That's all I need. After that, all of these guys are going to behave as intended. So I don't have a problem there. So that's putting delays. It's a lazy solution because it's still going to sort of not effectively use the pipeline architecture, right? So we want it to use the pipeline architecture effectively so that every instruction is getting done every clock cycle. Every clock cycle, one gets done. Okay, so any better way? Yeah, we talked about that. You do exit XMEM forwarding here, or you do a mem write back forwarding here. We have discussed all these things, right? Now, we have also computed all of these things, except there's one difference here. We wrote -20, but over here there's a slight confusion, 10 or -20, right? So the only reason why we can assume that it is -20 is because writing is happening in the first half, reading is happening in the second half, right? So one after the other. The only problem that can be is satisfying setup and hold time requirements. You're writing to something and then you're reading from it right away, right? So if it becomes too fast, if that access becomes too fast that you're not satisfying hold time requirements, then you can get into trouble. So except for that, we should be okay. That's why we can use -20. Otherwise, we would have to sort of delay that read a little bit. Questions? But apart from that, register forwarding, better idea. We need selection of this or this or this. We talked about those things and you guys sort of, I think you guys get it. Yeah? Okay, so that's your register forwarding idea. We need to check the destination register of a previous instruction and then the source of the current instruction, right? So if you are executing the first, second, and third, the destination of the first, is it the same as the source of the second or source of the third? Now we are going to try to classify it into different cases. Case one, we can say XMEM hazard. So it's first and second, right? The main instruction and the instruction after that. Or you can talk about the main instruction and the second instruction after that. 1, 2, 3. Write, use, use. Between this and this, if it is the same register being written to and used, you have XMEM forwarding can be used to solve X hazard. But between here and here, okay, mem write back, forwarding to solve mem hazard. Obviously, for all this to happen, the destination over here should be the same as one of the source registers here or one of the source registers here for X hazard or for mem hazard. Now we need some Boolean logic to implement this into a forwarding unit. Now when we start looking at the forwarding unit, we'll take a look at it as a logic, like if conditions, and also like a block diagram. We'll try to note what are the inputs and what are the outputs of that forwarding unit. Now, if the hazard exists, we are going to pass the needed values via the forwarding paths. So we are going to implement muxes, which will allow you to select straight through, no hazard, or feedback, right? Feedback from XMEM forwarding register, pipeline register, or feedback from memory write back, right? It's essentially a feedback, right? So 1 down or 2 down. Go ahead. Well, because for the instruction, it is getting a something that has not been written to ahead of time, right? But yeah, it's right. It's a feedback. It's actually something that is going back. But only if you look at it in terms of hardware, right? If you look at it as a instruction getting executed, for it is like getting a sense of a future, right? So that's why it's forwarding. The main reason is this is going forward. This is going forward, right? So if you look at it in terms of a pipeline diagram, the arrow is still pushing it up. You can never do this, right? You can never go back. You can only go front. You see that? But yes, if you look at it just in terms of hardware, there would be a connection going back like that. So it's technically a feedback. All right, so we need this, we need this, we need some muxes to do the job. Okay, so what are we checking? This should be sort of very easy to follow along if you guys are okay with the two hazard situations now. The two hazard situations and how do you solve them using the register forwarding. This is case one. What is that? Is the destination register of an instruction that is right now writing to the XMEM register, right? That's 1A. Destination register here, right? That's $2 in our example. That is right now it has just written to the XMEM pipeline register. Is that the same as IDEX? What is that? IDEX is the instruction after that, right? That instruction, it's source register. You see, if the AND instruction is right now here in the ID stage, at the same time, the instruction above that will be in the EX stage, right? At the same time, it will be in the stage above that. So whatever you are writing to the execute memory field, register RD field in the XMEM register, XMEM pipeline register, is that the same as the source register of the next instruction or the other source of the next instruction? So what is this? This would be $2 here. In our case, this is $5, right? But 1B doesn't meet here. In our case, what is happening is 1A is occurring. 1A is being satisfied. Register, you're looking at what? This guy, is it the same as this guy or not? Right? This is the XMEM forwarding register. XMEM. This is IDEX. In this guy, there is going to be a field for register RD. What is it? What is the value? If that is the same as in the IDEX, that IDEX has now moved here, right? Is one of the source registers for the next instruction. Is it the same or not? $2 there, $2 there. Yes, they were the same. You guys see that? Now, in terms of how we are writing this, XMEM, all of these are what? This is what pipeline register are you talking about? What field in the pipeline register are you talking about? This is register destination. First source, second source, right? If they are equal, in this case 1A is satisfied, we are going to get a detection. That's how we have detected a X hazard. X hazard is 1 and 2, right? Like with the next instruction. We have detected it over here. Similarly, you can write it for the need for memory write back forwarding. A mem hazard. Mem hazard happens when the instruction over here, you see, this is mem write back. The destination register of an instruction, which is right now in the mem write back stage, is it the same as one of the source registers of IDEX? So mem write back and IDEX, they are two back, right? So that's talking about the instruction that is two instructions out, 1, 2, and 3. So it's talking about 1 and 3. If an instruction is in the memory access stage, 2 instructions out, you would be in the execute in the decode stage, right? So that would be IDEX. First source, second source. If 2A gets satisfied or 2B gets satisfied or both get satisfied, then you have a mem hazard, which can be solved using memory write back forwarding. Again, it's the same thing. Which pipeline register? What field in the pipeline register? Which pipeline? What field? What all goes into that? What all goes into each pipeline register? How do I know? You have to sort of go back and take a look at this to get to know all the things that go on top of it, right? So for example, for IDEX, you're putting PC plus 4 and everything about the instruction. For that was for IFID. For IDEX, a bunch of control lines, read data 1, read data 2, 32 sign extension, the instruction from 20 to 16th bit, 15th to 11th position, all of those are going to that index, right? So what is this? RT, right? RS or RT. This is RT. This is RT or RD, depending on what type of instruction it is, right? So all of those are also being written onto the pipeline registers, along with all the bunch of control lines. Let's see. let me ask you this. Do I need to worry about register write control signal as far as this hazard detection unit is concerned? So you see, there is write, use, right? In order for write to happen, register write needs to be active, right? So one of the inputs to that forwarding unit should be register write, which is going to be what? Part of this guy, right? Part of the write back control signal. One of them is register write. Yeah? Right, over here we are using it. And that register write, if it is 0 for the first instruction, that means you are not writing. And if you are not writing, then there's no hazard. You're not changing the contents anyway. All right, let's see. We go back to, where were we? We did this. We talked about X hazard and case 2, mem hazard, right? So question here is the destination register of an instruction that is right now just written the value on the memory write back register, is it the same as the one of the source registers that have written their value on the IDEX field or not? And if it is, you have a mem hazard, and we can fix that using the memory write back forwarding. So two pairs of data hazards. The first two are execute hazard destination equals source, destination equals the other source or not. Then you have 2B. This is mem hazard. 1A and 1B can happen 1, 2, and 3. This is what write, use. Between these two, you can have this. And between these two, you can have this. Can I have a memory hazard without having an execute hazard? Can I have a memory hazard without having an execute hazard? I can have, right? That is also always there. So we can have something like this. Write to not 3 use. If you use the same register that you wrote to, you don't need to do any X mem forwarding, but you need to do a mem write back forwarding to solve this. Which is why you need two different muxes. One for the selection as far as this guy is concerned, one for the selection as far as this guy is concerned. Right? One for the XMEM and one for the memory write back. Yeah? All right, let's try to take a look. So a lot of information here. Let's try to go through them a little bit more in detail, slowly, right? So in terms of hardware, what have we added? Mux, wait, hold on. A mux here, a mux there. This mux was already there, right? So this mux was to select between RT and RD. That was the register destination selection, right? So that mux was already there. Yeah. So we have added here and we have added here. Two muxes. If you look at this, what are they selecting? No hazard, one type of hazard, the other type of hazard goes into the ALU. For the second input of the ALU, no hazard, one type of hazard, the other type of hazard, right? Or feedback from this guy or feedback from later, right? XMEM forwarding, mem write back forwarding. Those are going to be for two. Why? Because you have RS and RT, two sources going into the ALU. So we need to talk about the two muxes, how their selection is going to be. The selection is based on forward A and forward B. obviously we have to select between 3 options. So we need forward A to be 2 bits, forward B to be 2 bits. Now let's talk about this forwarding unit here. Forwarding unit has a bunch of inputs and only 2 outputs. What are their outputs? Forward A, forward B. What are the forward A and forward B control lines are you going to set to either do no hazard, so no, you don't need to do any sort of forwarding, you just go through as the instruction goes on, or you do XMEM forwarding, or you do mem write back forwarding. So that's the only thing that it is controlling as an output. But to determine the value of forward A and forward B, you need a bunch of inputs. You obviously need this, right? XMEM RD. What is this XMEM? It is the pipeline register. What is register RD? It is the field in that pipeline register, right? You need that as an input to forwarding unit. Why is that? To do that check. To do that check, I need that input, right? So because of this, I need that as an input there. Now this should open up all the other options. I need this, I need this, well, I already have this. I need this. What else do I need? I need this, right? So I need IDEX RS, IDEX RT, mem write back RD. Everything else I have. Yeah? Let's go back. Let's check. Mem write back register. So this is your mem write back pipeline register. Take the register RD field from here and put it as an input there. Next, we said even the IDEX, right? IDEX, RS and RT. Where are we getting that from? This is your IFID. This is your IDEX. You have put RS, RT, RT, RD, all of them on top of this IDEX pipeline register. There is RS, RT, another RT, RD, because you have not yet made that selection between the last two, depending on whether it's R type or I type instruction. For R type, you go RSRT, RD. For I, you go RSRT, RT. You have not made that selection yet. You are going to make it here, right? So all of those are going here, RS and RT. IDEX RS right here, IDEX RT right here. So those are inputs. 4 inputs we talked about in black. Now let's talk about the ones in yellow. You obviously need what? This guy right here. What is that? Are you doing the writing, register write, as far as the EXMEM is concerned or not? That would be the register that is the second one. Are you doing that with respect to the second one or not? And then this guy, is the register write active with respect to the instruction in the memory write back stage or not? So that would be 1 and 3. So 1 and 2 or 1 and 3. You guys see that? For both of them, it is the register write input. So all of those are inputs, and the only thing you have to compute is what should I forward? So now let's talk about which option corresponds to what. Let us do the easy one first. Let us take a look at this mux. This is your forward A mux. And you have something that is going straight through, right? So you read from the register file, put it on top of this pipeline register, you read the same place, and that becomes your input to the mux, and that is what goes to the ALU. That is going to be what? I'm going to call that no hazard. If there is no data hazard, then you don't need to do any forwarding. You just can go through as the instruction is going on. That would be there. Similarly, you also have that over here, right? Maybe that can be good. No hazard. If there is no hazard, then for both the inputs of the ALU, pass whatever was going through without this forwarding idea, right? That is, I think that is 0, 0, 0, 0. So if forward A control line to the mux, obviously we need 2 bits because we have 1 out of 3 selection. If it is 0, 0, then your source is IDEX pipeline register, and what you're passing is the first ALU operand comes straight from the register file, not from feedback. It is coming straight from the register file. The source is IDEX. How do you know that? Let's go back, take a look. This guy, where is this coming from? IDEX pipeline register. Yeah. So source is from here. This happens when there is no hazard. So I can say this. This is when it is 0, 0, right? When forward A, the select lines are 0, 0, that means that you have not detected any hazard and you are passing the thing that you already have from the IDEX pipeline register. As an explanation, it is whatever you have read from the register file. So that would, whatever you have for forward A here is the same for forward B here, right? So it's the same thing here. Forward B, 0, 0, IDEX. The second ALU operand in that case comes from the register file. So A and B, very similar. The only thing is, this is first operand here. First. This is second. That's the only difference. Next, let's talk about the other case. Here, what are we doing? If it is 1, 0, then we are doing XMEM forwarding. Let's try to take a look. If it is 1, 0, we are doing XMEM forwarding. Now let's try to track this line, this particular input, second input. Where is that coming from? If I go back, either here or here, but it is coming from memory write back. I see that? The source is memory write back. So if it, what is that? Memory write back is 0, 1, right? So if it is 0, 1, if forward A is 0, 1, then we are doing what? Memory write back forwarding, right? So as a schematic here, it is feedback. What is that? Whatever you have in the memory write back for that operation, for ALU A side, get it from there and then push this back as an input there, and then select. For this, what needs to happen? You need to have memory write back forwarding should happen only when 2A is satisfied or 2B is satisfied. Let's see that. In this case, we are talking about forward A, right? So we are talking about 2A, right? So this is, I can say, check 2A. That's depending on that check, you are going to pick that. Last option, 1, 0. What do you do there? You do the XMEM forwarding. Where is this coming from? Obviously, XMEM, right? So if I track back from here, is the XMEM pipeline register. So whatever you had for the ALU first input, forward that from the XMEM stage to the input of the mux, select that, and that goes through the ALU. If what? 1A is satisfied, right? So if I can say check for 1A here. If 1A is satisfied, then set forward A to 1, 0 and forward from there. And similarly, everything is the same for the second mux, forward B. No hazard, mem write back forwarding, check 2B, XMEM forwarding, check 1B for the selection of the second input for the ALU. And that's it. That's your forwarding unit. Your inputs are Destination register, check with one of the source registers of the next instruction and the instruction following that. Also monitor register write control signal. That's your inputs to the forwarding unit. Outputs, forward A 2 bits, forward B 2 bits, to essentially determine which of the three options get to the ALU. No hazard, straight through. There is X hazard, then we have what? X hazard is 1 0, X mem forwarding. Mem hazard, mem write back forwarding, set forward A to 0 1. Questions about this? All of this to do what? All of this to avoid a write use hazard. Write use hazard, that's it. Doesn't even fix the load use hazard. All right, let's see. We talked about this. Yes. Yeah. Proceed normal, forwarding, hazard case one detected. Yes. We talked about this. All right. So now let's talk about the forwarding logic. So this is going to be an if condition, essentially something that will determine our binary logic. So this is for the X hazard here. What is X hazard? First instruction and the instruction immediately after that. Does it have a hazard or not? What are you doing? You are first looking at the register write control signal. If it is inactive, then you don't have to go through anyway, right? You're done. There's no hazard. If that register write is 1, then you do another check. What is the second check? Make sure that you are not writing to register 0, right? So this is what? Whatever instruction is in the XMEM stage, the destination register of that is not equal to 0. Make sure that you are not writing to register 0. That's what that means. Because it's constant, it is supposed to be all zeros, right? Make sure you are not writing to $0. Register write should be 1. You should not be writing to destination. A destination register cannot be $0. Next, the instruction which is written things onto the XMEM pipeline register. The destination register in that, is it equal to the register, one of the, this is the first source register of the instruction after it, right? So if this is 1, let me use another color, 1, 2, write RD and then use RD, right? This RD is that. Is it the same as whatever you are using here or not? Use RD as an RS or as an RT, right? If they are, then what you have is a X hazard, can be solved using XMEM forwarding. So you forward A as 1 0. Source is XMEM. 1 0. Source is XMEM forwarding. 1A satisfied. Similarly, you can write the logic for the other case. The only thing what changes is what? RS, the check is for RT, the other source register. So register write should be active. You should not be writing to $0. Destination register should be the same as the source, one of the second source register of the next instruction. Then you also forward 1 0 for forward B mux. Hazard, X hazard, solution, XMEM forwarding. XMEM forwarding is essentially forwarding A and B as 1 0. Now, we can repeat the same thing for mem hazard, RD and RT, and set forward to 0 1 and 0 1, right? So mem hazard, if this was mem hazard, what would happen? You would be looking at mem write back register write. Mem write back register RD should not be 0. Mem write back RD should equal IDEX RS. Forward 0 1. Similarly over here, mem write back register write. Over here you will have mem write back register RD not equal to 0, mem write back register RD equals IDEXRT or not. If it is, then forward 0, 1. Right? That would be your next slide, case 2, mem hazard. Where is that? Oh, I'm not writing it there. But you can make that another slide, right? So let me just highlight where all you would make changes. Can I duplicate this slide? Current template after. Ooh, nice. Mem 2. This would be changed. This would change. This would change. This would change. Right? This would change. This would change. This would change. That would change. So wherever I have striked, it would become mem right back. I think that is it. Everything is the same. So that would be case 2. Yeah. So this is your data path with control with forwarding unit. In the next lecture, we'll add some more things to it, like a hazard detection unit. We'll try to place it over here somewhere. So more things are getting added to this later. Okay, so let's talk about some things that are a little bit more interesting than this. What is happening here? Take 1, take 2, add them, write to 1. Right? So it's a problem, and then there's another problem, and there's another problem after that, right? So you're writing $1 here, you're using and writing $1 here, you're using and writing $1 here. So it's not write, use, it is write, use, use. You guys see that? So this is write. To what? 1. And then you're using that right away. But you're also writing to it. And then in the next one, you're using it and you're writing again. Right? So $1 is appearing there, there. All right, so now let's talk about this. Let's suppose we did not know about these two. Let's suppose we did not know about these two. Then what would it be? It would be write, use. You could get it done, right? How do you get it? XMEM forwarding takes care of the first one. Mem write back forwarding takes care of the other, right? Good? Yeah? Okay. Now, because we are writing here and writing here, think about the third instruction here. What kind of forwarding should I do for the third instruction? Because if I was doing mem write back forwarding for the third instruction, I would be forwarding the new value based off of the first one. Go ahead. X forwarding for both of them, right? So if you have this kind of a situation where you are doing a write, use, write, so instead of doing it write, use, you're doing write, use, write, use. In that case, you don't do mem write back forwarding, you do XMEM forwarding. You see, compute A, forward XMEM. New value, forward, sorry, I should say forward here, and then forward here. Right? So you do XMEM forwarding. In other words, disable mem write back forwarding if that is the case, right? Just disable mem write back forwarding. What needs to happen for you to disable mem write back forwarding? What is that one thing that is causing this to be in this situation? This guy, right? That is the problem. If this guy was something else, we were going to be okay. But this is equal to what? This let me use a different color. this is a problem. If that is the same as this or this, like the second one, then you are going to have to do a execute mem forward, xmem forwarding instead of mem write back forwarding. In that case, disable mem write back forwarding if you have that situation. We are capturing that into our forward unit logic. So for the third one, do xmem forwarding and not the mem write back forwarding, because mem write back forwarding will be using the updated value here, but not the second updated over here. So we are going to have to use the xmem forwarding in that case. The problem is that the both type of hazard are affecting the same register, in this case $1. So we are going to enable mem write back forwarding because it's the most recent value. We are going to disable the write back forwarding. So from the register's perspective, from the pipeline register's perspective, we are going to be enabling the executing xmem forwarding, disable the mem write back forwarding. So for the case 2, go ahead. Right, so it's xmem and mem write back. Xmem, mem write back. So mem is the instruction is in the memory stage, the one that is being affected by both. Let's see. So we are simply changing case 2 over here to reflect this logic. So case 2 is what? Case 2 is this guy, right? That we just wrote. So we are rewriting case 2 with that modified logic here. What is that? First things first, register write should be active. Next, the destination register should not be 0 as far as the first instruction is concerned. Then you check for this. Then this should not happen, right? What should not happen? The register write for the one before should not, all of this should not happen. So if this is a 1 and the destination, so essentially what are we checking here? We are checking whether there is a X hazard or not, right? So it's like this, right here. We are checking if there is a X hazard or not. Oh, sorry. So, and if there is no X hazard, then you forward 0, 1. Because if there was X hazard between the second and the third instruction, you still do execute xmem forwarding. Don't do mem write back forwarding. So for mem write back, mem hazard, right? We are redefining this. We are redefining case 2. We are not redefining case 1. Case 1 is going to happen. Case 2, we are saying do this as far as you are not doing, you don't have that. If you don't detect X hazard even between the second and the third one. Go ahead. I couldn't hear the last part. Can you say that again? Instead of? Oh, okay. Sure, but you are going to have to check for these, right? Whether you are writing or not. So if you are writing, you can stop right there. Register write is equal to 0. You can stop right there. You don't have to go forward. So this is case 2, meaning you are looking at 1 with respect to 3, not with 1 with respect to 2. So 1 with respect to 2 already has all of those checks inbuilt over here. Is that your question about why are we? The green block in the last slide, right? So and not of this, right? So this is case 2. This is with respect to the third instruction, right? Mem write back. You're checking with mem write back. So you're saying if you're looking at this instruction with respect to this, You do mem write back forwarding, but not if these two are the same. Right. Oh, sure. Yeah, yeah. That is okay. That's just the way to express logic. Sure. Yes, you can do that. All right. So I hope that you guys had some interesting time with this. I think that's it. You guys can do the activity. Today's activity is easy peasy. What is that? Where is 00? So we have one more lecture on pipelining. We are going to be addressing load use hazard, and we'll also look at branch predictions. So we'll try to look at, hey, what if I just predict something based on statistics, and if it is wrong, I'll flush out my pipeline. So essentially, forgiveness is better than punishment. We'll try to play that algorithm. Go ahead. Case one? Case 1. No, we are going to have to use another unit for that. So this is forwarding unit is for specifically register forwarding. So load use hazard will be fixed by a separate hazard detection unit. Let's see. All right, I can stop recording here, and then I hope that you guys have a relaxing break. Today's activity is going to be like 3 seconds, and you will be done. Just be careful about the last instruction. And then I will see you guys on what, July 11th? July 11th, right. 12th? Okay, so I'll see you guys on July 12th. Happy 4th to all of you. Please be safe and also have some fun. You have a nice break to Arham. Was that?